طيب بسم الله الرحمن الرحيم. We started to talk about the digital transmission or broadband transmission, and in that case we're talking about representing the zeros and ones or the digital bits into analog signal, unlike the previous chapter where we talked about, chapter 4, we talked about representing the digital bits into digital signal. So here we're representing the bits into analog signal to facilitate the transmission of the composite signal over bandpass channel. We talked about ASK or on-off keying, and we have concluded the fact that the bandwidth required for the composite signal in the case of ASK was simply S times 1 plus D, where D is like a filtering factor, and it ranges from 0 to 1. And S, of course, is based on the bit rate, and R, which is the ratio between the data elements and the signal elements. The motivation behind the FSK, or the frequency shift keying, is the fact that always noise affects the amplitude much more than it does when it comes to frequency and phase. That's a well-known fact. So the noise attempts to vary the amplitude more than the frequency and the phase, which makes ASK more prone to noise. And FSK, or when we represent the zeros and ones by changing the frequency, this will make this composite signal more resistive to noise. So that was the motivation behind FSK. So FSK represents the 1 as high frequency sine wave and the 0 as low frequency sine wave. Okay? So we know if we have a sine wave signal like this, the composite signal will have a bandwidth of S times 1 plus D. Okay? However, because here we have two composite sine waves, one for 0 and one for 1, we need to separate the two from each other. And we separate that using the what we call 2 delta F. Okay? So 2 delta F here separates the frequency that represents the 1 from the frequency that represents the 0. 2 delta F is arbitrarily chosen so that we have some kind of a guard band between the two, because of the fact that at the receiver side, of course, as you can imagine, we're using some kind of filtering. However, these filters are never ideal. Okay, so we as you might have studied in signals, we always need to leave some guard bands between the signals so that we allow or we facilitate the efficient reception on the receiver side, because of the fact that these filters are not ideal. So this 2 delta F is what we use to separate the two symbols, or the two representations for 0 and 1. For each one of these, we have S times 1 plus D, which means that the bandwidth is S times 1 plus D plus 2 delta F. So what is the minimum bandwidth? Minimum bandwidth when 2 delta F is minimum. What's minimum 2 delta F? 1 plus D times S. Bravo عليك. Because we have here half times S1 plus D, and here half. So if we have no separation whatsoever, assuming that we have an ideal filter, of course in practice we don't, the minimum 2 delta F becomes 1 plus D times S, which makes the minimum bandwidth 2S times 1 plus D, right? So if I tell you, calculate the minimum bandwidth, I don't have to give you 2 delta F. I assume that you should already know it. If I tell you, using this bandwidth, calculate the maximum bit rate, I assume that you should be able to get what 2 delta F is.
Is it 1 plus D times S or 2S?
The minimum 2 delta F is 1 plus D times S. So the total bandwidth becomes 2S times 1 plus D. صح كده؟ Okay. So that's binary frequency shift keying. An example. So we have an available bandwidth of 100 kilohertz, which spans from 200 to 300. So this can be again drawn from 200 to 300 kilohertz. So the middle frequency is 250. Okay, type. What should be the carrier frequency? 250, alas. And the bit rate. Bit rate, huh? If we assume that we modulated our data by using FSK with D equal to 1. So we know that the bandwidth is 100K, right? And this is equals to S. What's S? N. ما احنا ما كلمناش على 2 delta F هنا. 2 delta F is if we assume the minimum 2 delta F, the minimum 2 delta F is S plus 1 plus D. S times 1 plus D, right? بس يعني خطوة خطوة. ال S اللي هي N times 1 over R. What's R? 1. So it becomes N, right? 1 plus D. D here is 1, so this is 2. Okay? Plus 2 delta F. I didn't give you 2 delta F here. So here in the example, he says that we will choose 2 delta F to be 50 kilohertz. Okay? So if this is 50 kilohertz, then N times 2 becomes a 50 kilohertz, so N becomes 25. Right? So N becomes 25.
Why did you put the 2 delta F as 50?
It's arbitrarily chosen here. In the example, it's arbitrarily chosen. Or if I tell you, I can make this a little bit more interesting and tell you what is the maximum bit rate that you can get. And I don't have to give you 2 delta F. What is the maximum bit rate that you can fit in this bandwidth? Is when 2 delta F minimum. The maximum bit rate becomes when 2 delta F is minimum, right? So, here the bandwidth, which is 100 kilohertz, equals to S times 1 plus D. It becomes 2N, صح?
Yes.
And what's minimum 2 delta F? It's also a 2N. صح كده؟ اللي هي S times 1 plus D. Right? So in that case, also a N is equal to 25 kilohertz. Which tells us that this 50 is actually minimum 2 delta F.
How do you
This-
get the 2N for the maximum?
For maximum bit rate, the 2 delta F has to be minimum. Right? For maximum bit rate, the 2 delta F has to be minimum. Because here the signal looks like this. We have this to represent the 1, and this represents the 0, and there's no space between them. Right? Which means that 2 delta F is the minimum. Minimum 2 delta F is S times 1 plus D, which is 2N. Right? Yes. Basically, they are close to each other with no separation in between. Okay? So the bandwidth becomes simply 4N. ماشي كده؟ طيب. In terms of implementation, we said that we can represent the ones and the zeros as NRZ. Okay? So we represent the 1 as positive voltage, 0 as 0, and so on. So what we could do, forget about this for now, what we could do is that to say, okay, we need to represent the positive voltage as frequency F1 and the negative or the 0 as frequency F2, such as F2 is much less than or less than F1, right? So what we could do is to say, okay, we'll input this NRZ signal. This is 1 and this is 0, and then 1, 1, and then 0. We'll input this on sort of a comparator. Okay? And then this comparator will sort of split all the positive values to this branch and the negative values to another branch, or the zero values to the other direction. So we'll end up here with a signal that looks like this. So we have positive and then nothing, and then positive, and then positive, and then nothing. Okay? And here we'll have nothing and then zero, or negative voltage, doesn't matter. And then nothing, and then zero. We get this, we multiply it with an oscillator. This oscillator will generate a sine wave with frequency f1. We multiply it by the positive, okay? Which means that it will generate a sine wave as long as it finds some positive voltage. And here, we will again multiply this by another oscillator with frequency f2, and then we'll get both values, and we'll sum them up to generate the signal.
One bigger than F2.
Yes, instead of we have two oscillators, one at f1 and one at f2. So we just need to do this separation before, and then multiply each one by the oscillator. And they don't do it this way. Why? Because if we do it this way, there is no correlation between those two oscillators, which will typically generate sine waves with some discontinuations here. Because the two sine waves that are generated are not coordinated with each other. So we end up having some discontinuation. We call this non-coherent. Okay? The non-coherent FSK does not guarantee any continuation between each bit and the one next to it. And if we implement it this way, typically we'll end up with non-coherent signal. And that's usually bad. Why is it bad? Because, well, remember, this continuation or sharp changes in the amplitude will generate high frequency components, or in some cases endless or infinite frequency components. And that's usually bad. Okay? So that's why they don't do it this way. They tend to use what's called a voltage-controlled oscillator. This voltage-controlled oscillator will generate a signal, a sine wave signal, with two different frequencies such that there is no continuation here. As you can see, in this composite signal, there is no continuation between each bit representation. Okay? So this voltage-controlled oscillator will maintain those two requirements. Will generate two different frequencies, but using coherent signal, which means that there is no discontinuation between the signals. So that's more efficient. So we tend to use the voltage-controlled oscillator for the case of FSK. That's in terms of implementation. Okay? An example. So we need to send data of 3 bits. So what's R here? 3?
Yeah.
صح. R is 3. Number of data elements divided by number of signal elements. So we need to represent 3 bits at a time using different levels, and the carrier frequency is 10 megahertz. Calculate the number of levels. What's the number of levels? 2 to the power 3, which is 8. But the different levels are represented by here. They are not represented by different voltage level. They are represented by different frequencies. So here we have 8 different frequencies. 8 different frequencies, right? We calculate the number of levels, so the number of levels is 8, and the baud rate and the bandwidth. Well, what is the baud rate? the baud rate S is N, which is 3 megahertz, 3 megabits per second, multiplied by 1 over R. So that's 1 mega A baud. So this is actually 1 megabaud. It's not 1,000. This is a type. Okay, so this means that the carrier frequency, so each frequency will have a range of bandwidth of 1 megahertz. Why? Because the D here, D is assuming that D here is 0. So, so the one frequency bandwidth becomes a S times 1 plus D. So this is 1 megahertz because D is 0, assuming that D is 0. Okay? So for one frequency, we have a range of bandwidths of 1 megahertz. And we need 8 of these, right? So I did not give you the value of 2 delta F, but I can simply slip a word here and tell you minimum bandwidth. If I slip this word, I don't have to give you 2 delta F. 2 delta F is implicitly S times 1 plus D, and D is 0, so it becomes S, and S is 1 megahertz already. Okay? So 2 delta F becomes also 1 megahertz, which means that there is no separation between the 8 symbols. So in that case, the signal will look like this. So around the 10 megahertz carrier frequency, which is the middle frequency for the entire composite signal, we have 8 different frequencies. So we have 4 here, and we have 4 here. Each one of these is 1 megahertz. And by having those 8 different frequency ranges, we can represent all the different combinations of these 3 bits. So this could be 000, 001, 010, and so on. Okay? So by having different frequency ranges, we can represent the different bit combinations. That's because for FSK, we have to represent the bit representation at different frequencies. Okay? So that's how the composite signal will look like. So that's the final product. So that's the composite signal in the frequency domain. And around the 10 megahertz, we have 1 megahertz, which means that from here to here, we have the middle frequency of each one can be calculated easily. It's 1 megahertz apart. Okay? And that's assuming that 2 delta F is minimum, which means that 2 delta F is also 1 megahertz. Okay? Any questions?
D is 0, right?
Eh?
D is 0.
D is 0, assuming that D is 0, yes. Assuming that D is 0. Okay, so again, so the motivation behind FSK was the fact that the frequency, changing the frequency is more resistive to noise more than changing the amplitude. So changing the amplitude tends to be prone to noise. Okay? What is the cost that we have paid for FSK?
That we need to keep some space.
Yeah, and
More bandwidth.
the bandwidth itself, the total bandwidth is much more.
Yeah.
It's minimum double. It's minimum double for actually representing the 0 and the 1. We have to have at least 2 times S 1 plus D. That's assuming 2 delta F is the minimum. Okay, so with minimum 2 delta F, the bandwidth at least double. Okay, so that's the cost that we have paid. So the question is, can we use another property which is, again, more resistive to noise, and we can have or maintain the bandwidth to be less than the bandwidth of FSK, and that turns out to be PSK. The phase is also one of the properties that is more resistive to noise. Okay, so the noise changes the phase with much less probability compared to changing the amplitude. Yeah, changing the amplitude. Okay? So the way that we use PSK or phase shift keying is to represent the 1 as a sine wave with phase shift of 0 and the 0 with a phase shift of 180 degrees, which is a minus sign. So as you can see, the PSK signal is inherently non-coherent. Right? صح كده؟ So it's inherently non-coherent. And we need to do this. We need to have this non-coherence because the phase at each boundary of the bit is what we rely on to detect whether this is 0 or 1.
So what do you mean non-coherent?
Non-coherent معناها إن هي it's not necessarily continuous. So you have some discontinuations at different points. You may have some discontinuation at different points, which means that the signal itself is not a continuous. Okay? And again, this discontinuation, as we said before, it generates high frequency components, right? So although the bandwidth is still the same because we have the same frequency, so the sine wave itself has fixed frequency, right? But the D factor typically is higher in the case of phase shift keying. Typically is higher. But again, I mean, it's not double. So still here the bandwidth is 1 plus D times S, which is good. So it's similar to ASK, but typically D will be slightly more. Why? Because these discontinuations requires high frequency components, and we need to really maintain this discontinuation because that's how we rely on to detect the zeros and the ones. So we need to maintain some of this discontinuation to be able to detect the zeros and ones at the receiver side. But in terms of bandwidth, it's 1 plus D times S, which is good. It's better because it's not double like the FSK, okay? Even if the value of D is slightly higher, it's still not double, because D is always from 0 to 1, okay? So that's good news. So it turns out PSK is a good compromise between ASK and FSK. It's a good. In terms of implementation, another piece of good news that the only thing we need to change is just to use polar NRZ. So instead of using positive and 0, we just need to because one is sine and one is minus sine, right? So for the case of binary PSK, we just need to represent the 0 as negative voltage, which is the polar NRZ. Other than that, the oscillator still generates one frequency, right? And then we multiply this by the polar NRZ, and our job is done. It's very easy.
What if we want to represent more than one bit?
Yeah, so that's okay. That's next. Okay. Type. What about QPSK? What about QPSK? For QPSK or quadrature phase shift keying, in that case we have 4 different levels. And here each level is represented by different phase, not different frequency or different amplitude, which means R equal to 2. So the way we do that is by splitting the bits into 2 binary phase shift key by simply using one splitter which splits each 2 bits into different directions. And then each one will be the polar NRZ. So we take the first 0, we put it here as 0, so 0 is represented by negative. And then we leave this one and we take the 1 here. So 1 becomes 1, positive voltage, and then 0 becomes negative voltage, and then 1 becomes a positive voltage. And then we take the even bits. The even bits will be represented here So the 0 becomes 0, and then 0 becomes 0, and then 1, and then 1. So we will split these into two polar NRZs. Okay? We will use one oscillator with one frequency. Okay? So we are maintaining the same frequency. So this oscillator will generate, on one side will generate a sine wave with frequency, with phase shift 0. And all we need to do is just, on the other branch, we will generate a cosine wave, not a sine wave. So we will have a phase shift of 90 degrees. So this will allow us to generate two binary phase shift keying, but the only difference is that one of them is shifted pi/2. Okay? So it's two binary phase shift keying, but one of them is shifted 90 degrees. And then we get the summation of the two. That's all we need to do. Okay? So the phases that will be generated here is minor. Remember, when we add or when we sum two sine waves, we don't simply sum the phases. يعني a sine wave with phase shift 0 and a sine wave with phase shift pi/2, the phase shift in the output signal is not pi/2. Okay? It's not simply pi/2. So these are the phase shifts that we need to that will be generated at the output signal. Okay? So by having two binary phase shift keying summed together, we can generate QPSK. All we need to do is just to shift one of them pi/2. Okay? Which means that pi/2 is the distance between one symbol and the other. يعني the one sine wave will, if we start from 0 phase shift, then the next symbol will have a phase shift of pi/2 and then 180 degrees and then 270. Okay? It turns out here we're not starting from 0 phase shift. When we talk about QAM, we will visualize this and it will become clearer. Because as I said, just by summing two sine waves, we don't simply sum the phases. No. Okay? So here, we start from 45 degrees. Okay? We start from 45 degrees and then 130 and then minus 135 and then minus 45. So these are the phases that will be generated at the output. And we'll talk about the IQ diagram. It will become clearer now.
So if you have 3 bits, would you start from phase shift 0? The second wave will be 45, and the third wave will be. Second wave will be pi/2, which is 90.
لا مش 90 بقى. انت لو قلت 8 يبقى pi/4. صح؟
Yeah.
انت you have 2 pi. You have 2 pi, صح؟
Yeah.
360 degrees is 2 pi. If you want to divide that by 8 different symbols or 8 different phases, then you have a distance between each two pi/4, right? So if you start from 0, then pi/4, then pi/2, then and so on. Then 3 pi/4 and then وهكذا. Okay? Okay, so find the bandwidth for a signal transmitting at 12 megabits per second for QPSK, and the value of D is 0. Of course, this is not typical. The value of D is higher compared to ASK, but this is just for example. So we need to calculate the bandwidth for this bit rate. So we can calculate S. S is N times 1 over R. What's R here? R here is 2, of course, because we're talking about QPSK. For QPSK, each 2 bits will be represented by one signal element, so R is 2. So this is a 6 megabaud. Okay. S is signal rate. The measure or the unit is megabaud. So simply in that case, the the bandwidth is S times 1 plus D, and D is 0, so the bandwidth is equal to S. طيب. So historically we have talked about two ways of representing a signal. We talked about the time representation of a signal, and we looked at the sine wave. We talked about the frequency representation of any signal, which is the frequency spectrum of a signal. We talked about these two a lot, right? There is another way of representing analog signal using what we call the IQ diagram. And the IQ diagram is another way of representing these signals using, in that case, dots. Using just dots. Okay? And as we will see, this way of representing the signal will allow us to visualize the signal in a more efficient way. So if we talk about an example, we have a sine wave which starts from with a phase shift of, let's say, hina, pi over 6. And then the sine wave continues like this. Okay? This sine wave has a peak amplitude of A. This sine wave in the IQ diagram will be represented by one dot. This dot will be put on the IQ axis such that the distance between this dot and the origin is A, and this is pi over 6. Okay? So this sine wave will be represented by a dot in the IQ diagram. Why do we need to do this? It turns out this IQ diagram allows us to, again, similar to frequency spectrum, which allowed us to understand many properties about the signal that we could not otherwise get from the time representation. The IQ diagram will also help us to understand some other properties of the signals which we could not do in the frequency and the time domains. To appreciate this, we can look at representing the techniques that we talked about so far in the IQ diagram. Exclude the FSK for now because the IQ does not really represent frequencies in any way. Okay? So the IQ is only used to represent amplitudes and phase, not the frequency. The frequency is not concerning us at this point. So for OOK or on-off keying, we are generating two sine waves. One, each of these sine waves have a phase shift of 0. So that's why they are on the same x-axis or the y-axis. Okay? One of them is 0 amplitude, right? Because it's on-off keying. And the other one with an amplitude of A. So the on-off key can be represented simply by two dots in the IQ diagram. The BPSK is represented by a sine wave and minus sine wave. And the minus sine wave will have a phase shift of 180 degrees, right? Yeah. So these can be represented by two different dots in the IQ diagram. Okay? The quadrature phase shift keying, the one that we have generated, started from 45 degrees, right? And then 135, and then minus 135, and then minus 45 degrees. So we have 4 different symbols. All of them have the same amplitude, but different phase.
We have 3 bits, so we'll have 8.
8 of these, yes. We'll have 8 of these, yes. So we will start from, if we start from 0, we'll have something like this, and then this, and then this, and then like this. Okay? So from the IQ diagram, we can look at these signals. That's why actually we have mentioned the fact that ASK, from here we know that ASK is more prone to noise. Why? Because if we look at the receiver, the symbols that we generate using these representations at the receiver side they will add some noise. The noise effect can be represented on this diagram very easily, that around each one there will be some dots like this. So if we see it on the oscilloscope at the transmitter side and at the receiver side, at the transmitter they're ideal. We see 2 dots. All the generated ones and zeros, there will be 2 dots. At the receiver side, we will add the effect of noise, and each one of them will become like a cluster of dots due to the noise. And here will be the same thing at the receiver side. So as you can imagine, these 2 clusters can overlap in the case of ASK easily. Whereas here, if we do the same effect of noise, right? The effect of noise is not that major because of the fact that in the phase shift, the 2 symbols, they become very far apart. You had a question?
In the QV escape, 2, why is it minus 450?
Minus 450?
Minus 35.
لا هو دي 45 degrees, sorry. Okay? So from the IQ diagram, we can sort of appreciate more and we can visualize why the BPSK is more resistive to noise, because the effect of noise will add some effect on the phase and the amplitude, but the clusters, they are still very far apart. Okay? So from here as well, we can see that here the clusters are a little bit closer. So the more dots we have on this IQ diagram, the closer they become, okay? And in that case, the effect of noise will become more and more. However, keep in mind that by doing this, we are increasing the value of R, which reduces the bandwidth. Okay? So by adding more bit representations, we are increasing R, which means reducing the bandwidth requirements. So it's a trade-off. When we increase the number of symbols, we increase the number of dots in the IQ diagram. We are increasing R, we're reducing the bandwidth required. However, by doing this, again increasing the number of dots in the IQ diagram will make these symbols closer to each other, so the effect of noise becomes a more evident and more significant, and that will add to the probability of error.
We can modify the amplitude to be higher, so we'll have more space.
That's exactly what we are going to do. So the question now is, why stop at this point? Why not think about combining the phase and the amplitude together to try to distribute these dots in the IQ diagram in a more efficient way? Can we do that? Yes. And that's the idea behind what we call quadrature amplitude modulation. So quadrature amplitude modulation, the Q here refers to the phase and the A refers to the amplitude. So we are actually combining the phase and the amplitude both together. So we can do it this way. If we do it this way, which means that we're using one quarter of the domain, and in that case, we'll end up with a sine wave of amplitude 0, phase shift 0, and we have different phase shifts for the different symbols. But this will make the effect of noise more significant. Why? So we can do it like this. So in that case, we will have the same amplitude for all the signals with different phase shifts, and that turns out to be more noise resistance. But if we want to combine the two, we can have something like this, which is a 16 QAM. So for 16 QAM, we can have 16 different sine waves, okay? And we can change amplitude and phase or phase to generate 16 different symbols, and each of these symbols will represent a bit combination of 4 bits. And we have 64.
But the bandwidth would be very small, right?
The bandwidth will be very small, but what is the risk here?
Yeah.
The effect of noise becomes like لأن هنا the distance between the symbols becomes closer and closer. Okay? Or if you want to make them far apart, you have to spend more energy to make the sine wave amplitude very, very high. But this will mean that you have to spend energy. right? So you have to pay a cost of some sort. If you want to be bandwidth efficient, you will be more prone to noise. Okay? If you want to be more resistive to noise, you have to spend more energy. So nothing comes for free. ماشي كده؟ So the main idea here is that we combine the amplitude with the phase to have more degrees of freedom, which allows us to address the trade-off between bandwidth efficiency and noise resistance.
What is the most commonly used now?
16 and 64. So typically, we use 16 QAM and 64 QAM. Okay? Any questions? So that's this section. In this section, we talked about representing digital bits into analog signal to facilitate the broadband transmission over a bandpass channel. So in chapter 4, we talked about representing bits into digital signal to facilitate the transmission over baseband channel. صح? And then in chapter 5, we talked about representing the same bits into analog signal to shift it in the frequency domain and transmit it over a bandpass channel. What is an example of a bandpass channel?
Radio.
Any wireless. Any wireless is a bandpass channel. What else in wire? Do we have an example?
Broadband wire?
Yes.
No,
حد فاكر؟ We talked about it. It's not that we did not mention. We talked about it. يا برافو عليك. شوف الراجل صح ازاي. So ADSL sends digital data over telephone lines. So in that case, we have to shift the data transmission in the frequency domain to be in the baseband, in the bandpass range, not in the baseband range. Okay? So that's what we talked about so far. So here we will talk about the fact that the signal, the input signal itself is not zeros and ones. It is in fact analog. So an example, our voice is an analog signal. صح? By default, our voice is an analog signal. The TV signal is an analog signal. So someone might say, yeah, but we have digital TVs and we have digital music and so on. Yeah, that's because we take a signal which is inherently analog. We use sampling, ماشي? And take these samples, convert it to bits, and then deal with the bits. That's one direction. Okay? So we talked about how to deal with this in the previous sections. So one route is to say, take the voice signal, sample it, these samples converted to bits, and these bits representing using broadband transmission or baseband transmission. Okay? Broadband in the case of baseband channels and baseband in the case of baseband channel. Another way of thinking is just to deal with the analog signals as they are and use what we call in that case not by a phase shift keying or amplitude shift keying, we call it a modulation. So we call it amplitude modulation, frequency modulation, and phase modulation. So we are still working on the three fundamental properties of any signal: amplitude, frequency, and phase, right? But this time the input signal is analog. ماشي كده؟ So these are the three classes of modulation. So when we see the word modulation, we know that the input signal is analog. When we see the word keying, phase shift keying or something like that, so this means that the input signal is digital signal. ماشي؟
So that was digital modulation.
This is called digital modulation, yes. So for amplitude modulation, the input signal itself is analog, as you can see. So in that case, similar to what we have done, nothing changes. Similar to what we have done, we have a carrier frequency with fixed frequency. And again, same implementation, oscillator and the input signal. The difference, the main difference here is that we used to characterize digital signals with bit rate and signal rate, صح? فاكر? In analog signal, we cannot do that. We characterize this signal by its own bandwidth. For example, our voice signal زي ما قلنا قبل كده كتير, it has a bandwidth of 4K. So our voice is by default an analog signal with a bandwidth of 4K. If we want to characterize this signal using signal rates and so on, then we have to sample the voice, convert it to bits. Then we can characterize the digital signal using signal rate and bit rate and so on and so forth, right? But here we're not doing that. We're just dealing with the signal as an analog signal, which means that the analog signal is characterized by the bandwidth, the baseband bandwidth of this signal. ماشي كده؟ So it turns out the Nyquist theorem also applies here, but instead of relying on the sampling rate, we will rely on the bandwidth of the input signal itself. And it turns out for AM modulation, the AM signal will have a bandwidth of double the bandwidth of the input signal. Okay? So when we have an analog signal of bandwidth B, the AM modulation will generate a composite signal that looks like this with a bandwidth of 2B. At the receiver side, as you can see here, it's a sine wave with changing amplitude, which is the result of multiplying the input analog signal with an oscillator that generates a sine wave with fixed frequency. So the output looks like this. At the receiver side, we just need to detect the envelope of this signal. We detect the envelope of this signal. Why is it double B? What Nyquist did is that he found that actually for each bandwidth of the analog signal, there is like some sort of a mirror analog in the negative frequency. This negative frequency, when you shift the signal in the positive side, it has a significance. So in the baseband, we tend to deal with only one bandwidth part, but when we shift it in the frequency domain, we have to consider the fact that this signal will have two parts, so it becomes 2B. So that's the reason that really the AM modulation, when it shifts the frequency in the positive side, there is a cost that you have to pay. That B becomes 2B. Okay? So that's the AM modulation. So, so in that case, it's very simple. Again, we generate sine wave and we multiply it by the input signal as it is analog. And so that's the formula. It's very simple. Directly. Okay? So the 4K becomes 8K. And in that case, in AM radio, as an example, for radio, if you switch to AM deals with analog broadcast of the voice, and it ranges from 530 kilohertz to 1.7 megahertz. Okay, and as we said, our voice has a bandwidth of 4K. Where is the 10K came from? The bandwidth of each channel now is 10K. Why is it 10K about?
Reduce the noise.
You have to maintain the 2 multiplied by the main bandwidth, which is 8.
Okay.
So we can maintain the 8.
حلو كويس. Our input signal, which is voice signal, is 4K. So for AM modulation, we need it to become 8K. صح? So the 4K bandwidth of the input signal for analog modulation becomes 8K, right? This is from the 10.
That's for the noise.
Bravo عليك. So the guard bands. Guard bands. So here, actually this signal is 8, but we have to leave some guard bands here and there. So it's 1K here, 1K. Why? Because when we tune, we use a filter, right? When you tune, we change the middle frequency of the filter. صح? When you change the radio channel, what you are essentially doing is that you are moving the filter middle frequency. But this filter is never an ideal filter like this. Filters are never ideal. So you have to have some effect like this. So that's why you need to leave some guard bands so that you can facilitate the efficient reception at the receiver side. Okay? Any questions? So that's M or amplitude modulation. For FM, we are changing the frequency of the output signal proportionally to the amplitude of the analog signal. This is what we call it the beta factor, which is dependent on the variation in the frequency and the amplitude of the signal. This factor typically is between, we don't have to memorize this, but typically and practically is between like 4 to 10. It's not like the D. Okay, and again, this beta depends on the variation in the frequency that you use in the output signal in relation to the amplitude of the input signal. So this can be very high or can be a little bit low. So typically we use beta in the range of 4 to 10.
In the frequency modulation, do you think that the maximum frequency would be the carrier plus the highest amplitude of the frequency, right?
The maximum amplitude of the carrier?
No, the maximum amplitude of the signal plus the carrier frequency.
Yeah, but remember, the composite signal generates a frequency proportional to this maximum amplitude of the signal. So definitely, in the transmitter, we have to limit the range of the amplitude of the signal because we cannot take an infinite amplitude and represent it using a frequency. So we have to have a limit, right?
Carrier plus minus the amplitude, the maximum amplitude.
لا ما هو احنا we are generating a frequency. So the bandwidth is based on the middle frequency, and we have some frequency on the right hand side and some frequency on the left hand side. This difference in the frequency is proportional to the amplitude of the signal. But أنا بقول لك proportionally يعني إيه؟ Proportionally يعني this frequency is proportional to the amplitude, صح? Okay, so يعني the frequency is equals to alpha times A. This alpha can be anything. This alpha is actually the beta. Okay? Proportional, Mahana, I can make it 1000. I can make each one voltage difference 1000 hertz or 1000 kilohertz. So? And I can make each one voltage 1 hertz difference. So it varies. It varies. Okay? And typically this beta is in the range of 4 to 10. ماشي كده؟ generalization and it's an approximation طبعا يعني احنا هنا we're talking about يعني typical bandwidth. Okay? Beta is arbitrarily chosen and it's given يعني I'm not going to tell you calculated based on كذا لا يعني it's given. I will give it to you. Slide. So if you have an analog signal like this, the output will generate an FM signal which looks like this. As you can see, from here to here, the frequency is high because the amplitude is high. And then As we go this way, the amplitude is low, so the frequency turns out to be low. This voltage-controlled oscillator will do this, will maintain this such that the signal is coherent. As you can see, we are changing the frequency higher and lower, but we are maintaining the coherence of the signal, which is good. So the signal is continuous. So that's good. And that's what this voltage-controlled oscillator does. So we input the signal, and the voltage-controlled oscillator will generate a frequency at the output signal proportional to the amplitude of the input signal. And as you can see here, the amplitude of the composite signal is the same. ماشي? The amplitude of the composite signal is the same. So it turns out that the bandwidth of the FM signal is not just double the bandwidth. There is a factor which we have to assume it. Okay? So that's the FM. No. لا ما هو 1 واحنا we have 1 plus beta, right? So beta is. So if we look at the FM radio بقى, the FM بقى اللي هو the other band of the radio, first of all we notice that the voice quality is high, صح? Right, because the effect of the noise is not as significant compared to the amplitude modulation. But the cost that we are paying is huge. How many times this bandwidth is compared to AM? 20 times. 20 times. What is the value of beta here? Yeah?
19. 1 plus beta, so 19.
So 1 plus beta becomes 10. 10 times 2 becomes 20. 20 double the AM. Which is, so the cost that we had to pay is huge. Right? and this is a typical value for beta. As I said, it ranges between 4 to 10, something like that. And of course, the higher, the better the quality will be in terms of يعني voice quality وكذا. بس طبعا انت you are increasing the bandwidth. Okay? So these nose stations they are not necessarily يعني nose stations. Because remember, the FM, there's no worldwide standard for it. It's regional. يعني when you move from one place to another, it changes. يعني I'm not sure if you have tried to drive cross countries ولا حاجة زي كده, but in some cases you can find some channels they change. So these might have some channels, these might have no channels depending on the regions. Okay, but the FM range is really very long compared to, يعني it's in the range of tens of kilometers. The FM range. That's because we are talking about relatively low frequency. Anyway, these are details, يعني, but that's the idea behind FSK. Any questions? Okay. So we'll stop here عشان احنا وقفنا في البناء.